The following video demonstrates the Mathers hydraulic fluid coupling and hydromechanical torque amplifying transmission technologies. Using Mathers' patented vane pump technology, we are able to produce a freewheeling clutch with torque control and amplification. The images show the principle of operation. The image on the left shows the vanes restrained in the rotor, preventing pumping chambers from forming. This is freewheeling or neutral. On the right, the vanes are released, allowing oil to be pressurized against the ring contour, creating rotary force on the ring. The ring is connected to an output shaft and allowed to rotate. Torque in hydraulics is pressure times displacement. As the displacement is fixed, controlling pressure controls output torque. Here we see a conventional vane pump with dowels to prevent cartridge rotation. This image shows the same cartridge with the dowels removed. This drawing is a cutaway of a fluid coupling assembly. The input drive shaft and rotor assembly rotate as one. The ring and end plates rotate with the output shaft. If the vanes are retracted, there is no transfer of energy to the output-driven shaft. If the vanes are released, energy can be transferred to the ring and output shaft via pressurized oil. Oil pressure can be remotely controlled to adjust output torque.
To test the fluid coupling, we've got it set up to a 15 kilowatt electric motor through a flexible coupling. This is the fluid coupling, Mathers fluid coupling. This gauge indicates the pressure that's inside the coupling. We have another drive coupling then, which connects to just a load cell piston pump in this particular situation. So I can increase load on the coupling by increasing pressure or flow or both out of our load cell pump. This is showing flow in litres. This is showing the pressure that's we're applying to the outlet of this pump. As this pressure goes up, of course, the amount of torque required through our coupling will increase, so this pressure will increase. PSI in the coupling. 1181 in. 1123 out. Just running the unit now at 2000 RPM. Increase the load in the coupling to 1000 PSI. Input speed is 1959. Output speed is 1884.
You have just witnessed a hydrostatic torque converter, or fluid coupling, running at 96% efficiency. To further demonstrate the operational principles, the following footage shows this same efficiency with a fan drive. In this demonstration, the coupling drive is attached to a standard Mack truck fan blade and double-ended variable speed electric motor. Here we see it in freewheel mode, with the fan blade being held stationary while the electric motor speed is increased. As the fan is released, frictional forces start the fan blade spinning. When the vanes are released, power is imparted on the fan blade, as we can see in here. When the vanes are recaptured, only frictional forces are imparted on the fan blade. As we remotely control the pressure in the coupling, we control the amount of output power that is transmitted to the fan with very high efficiency. This is a coupling cartridge that can be used for fan drives like the one just demonstrated, or for any of a myriad of drives that require a soft start, torque control, and drives up to thousands of horsepower. These drives can be mechanically locked up where higher power draws are required to eliminate all slippage. This is the theoretical power formula for the transmission drive. This indicates transmission drive, input speed and torque equals output speed and torque. This is torque amplification mode. Speed decreases and torque increases, maintaining constant power. This is transmission drive with power regeneration as standard. You can also select front-wheel drive features for snow, mud or sand, military vehicle, buses, etc. This eliminates the need for constantly running four-wheel drive transfer case. Furthering this technology, a typical transmission drive with hydromechanical torque amplification and power regeneration in a single drive is demonstrated. This is not a concept, this is an actual live working demonstration.
When I start the system up, I'll start it up with the Baines plant, which means the input shaft will spin and the output shaft won't. $11.99 on the digital tachometer, and the output speed, as you can see, is nil. And instantly we have drive straight through the coupling. We'll take it up to 70 bar, 1,000 PSI. As you can see, the pressure is climbed inside a torque converter. By reducing the displacement of the motor, the speed will increase, our pressure in our coupling will increase, our flow will increase. We're at zero angle on our variable motor. As I increase the displacement of the motor, speed decreasing, torque is increasing. Now to demonstrate the effect of speed, moment, we're 1191 in. We're 723 out. While reducing the motor displacement, speed increases. 850, 875, 1177. Now at this time, both shafts are spinning at virtually the same speed.
What you have just witnessed is what we and many international experts believe to be the transmission drive of the future. As shown in the table is a theoretical gearshift comparison between a conventional 9-speed manual gearbox and a Mathers hydromechanical transmission coupled to a 5-speed AMT. As you can see on the Mathers transmission, engine speed variations are considerably lower and has a relatively constant power draw, allowing engine management systems to maximize fuel efficiency. This concludes the presentation of the Mathers fluid coupling and hydromechanical transmission, the transmission drive of the future. The practical applications for these technologies are virtually limitless, and able to be licensed by innovative designers. Every feature wanted in a transmission drive is incorporated into these designs. High-efficiency compact torque converter, torque amplification for all gears, power regeneration for all road speeds, variable pressure control of torque to eliminate torsional shock, programmable power on demand for four-wheel drive. Other uses for the coupling include as a fan drive power regeneration system at highway speeds, disconnectable drive gears to eliminate parasitic loss from alternators, compressors and turbochargers. Undoubtedly, the first innovators to use this technology will be able to find a myriad of applications. The question is, are you up to the challenge? For R&D and/or manufacturing licenses, contact Norm Mathers or Rob Price at Mathers Hydraulics.